Hi, and welcome to another online lecture for General Physics 2. This one is dealing with the topics of reflection and refraction and introducing us to image formation. We'll continue talking about the formation of images in the following presentation as well when we talk about lenses. So we transition from talking about waves of light to rays of light. How do we get there? Well, surfaces of constant phase, and that just means places on the wave where the wave height is all the same, are known as wave fronts. If I have a little pulsating sphere making waves, these spherical shells would represent the wave fronts of those waves produced by that pulsating sphere. The distance between two wave fronts is the wavelength of the wave that is being produced. And we can draw radial lines through those wave fronts outward from the source, and we're going to call these rays or rays of light. And we're going to think in the next presentation about what happens to rays of light when they pass through various materials. Turns out that we do this for convenience. It's easier for most of us to think about what happens when a ray of light encounters a mirror or a lens than it is to think about what happens to the entire wave of light. Far away from the wave, rays are essentially parallel to one another. So if you're close to this pulsating sphere that's making the wave, the rays are all diverging out from one another, and the wave fronts themselves are pretty curved. But if you get farther and farther and farther away, the rays get more and more parallel to each other in any small area that you're looking at. And that means the wave fronts are relatively planar at that point. Why do we care about parallel rays? Well, it turns out that when we talk about how light interacts with a mirror, we often are talking about how the rays that are parallel to one another behave relative to that mirror or lens in the next presentation. So first, we think about what happens when these rays of light encounter a mirrored surface, and we deduce something called the law of reflection. So in my diagram, I have an incident ray of light that's coming in and striking the mirror at this point. And I have a reflected ray of light that is leaving that same point. And we measure an angle of incidence as the angle between that incident ray and a line that is perpendicular to the mirrored surface, called the normal line. We measure the angle of reflection similarly. The angle between that reflected ray and the normal line is called the angle of reflection. And we arrive at what is possibly the easiest model in physics, the fact that the angle of reflection is equal to the angle of incidence. This is true, by the way, even if you don't have a planar surface like we have right here. If the surface is curved, that's fine, as long, again, as you construct a normal line to the surface at a particular point. The law of reflection will apply to curved surfaces as well. So if we send in a bunch of parallel rays of light to a perfectly flat surface, they'll all bounce off at the same angle as each other, and they'll remain parallel to each other on the other side. And this is specular reflection. If, however, you have a bumpy surface, and it doesn't need to be visibly bumpy per se, but if you were looking on the microscopic level, the surface would look bumpy. Then the rays of light that come in parallel to one another all get reflected. They still follow the law of reflection at each individual reflection point, but because those are all different angles, the reflected rays are all at different angles relative to each other as well. And so this is an example of diffuse reflection. But let's start by talking about what happens when we look at ourselves in a flat mirror known as a plane mirror. If you face yourself in the mirror and look, you raise your right hand, the image of you that's formed behind the mirror appears to raise his left hand, and so we're, most of us, familiar with the idea that mirrors seem to flip the picture of us around when we're looking at it. So images in plane mirrors have three properties that we can note, and we're going to talk about them here with the plane mirror, but then also talk about these properties with images formed in spherical mirrors and later in images formed by lenses. And that is, the image here is upright, meaning that the image is oriented the same as the object, in this case the person that is forming the image. The image is the same size as the object in this case, and the image is located as far behind the mirror as the object is in front of it. And we're going to call those image and object distances shortly. Images in plane mirrors are also said to be virtual images. What do we mean by a virtual image? Well, we mean that if I have an actual rook from my chess set here and light is coming off the top edge of that and striking the mirror, it's following that law of reflection. So the angle of incidence equals the angle of reflection, and that light ray is bouncing back into the eye of an observer. However, to the eye of an observer, that light appears to have come from some location behind the mirror, and so we can sketch the apparent ray or the apparent path that the light ray took behind the mirror. If you shift your eye slightly to a little bit different angle, you can think about another ray that comes off of this, strikes at a nearby location, but is reflected at a slightly different angle and comes into the observer's eye. Well, those two rays, if you extend them backwards behind the mirror, show you the apparent path that the light has come from, and those two lines will come together behind the mirror at the location where the image is formed. This image is said to be virtual because it's formed where rays of light appear to have come from, but there is no actual light converging at that point. Images in plane mirrors have the property that the object distance is equal to the image distance. We're going to deduce that from geometry here. If you do not care about geometric proofs of this, feel free to skip ahead to the next slide. So the object distance is equal to the image distance. How do we establish that? Well, if we look at our diagram and we switch the rook out for a knight, light that leaves the bottom edge of the knight and travels up to the mirror and then is reflected back into the eye of the observer will follow the law of reflection, so the angle of incidence will equal the angle of reflection here. Furthermore, this angle of incidence plus this complementary angle, beta 1, together form 90 degrees since they lie between the normal line and the mirror itself. On the other side of the mirror, beta 2 and alpha also must combine to form 90 degrees because they're again between the mirrored surface and the normal line. If alpha equals theta, which they do because these are opposite angles of two lines that intersect, then we know that beta 1 here has to equal beta 2. If beta 1 equals beta 2 and they share a common side, and then the angles down here are both 90 degrees, these are congruent triangles, and that means that the triangle formed by point A, point B, and point C is congruent to the triangle formed by point D, point B, and point C. And therefore, the object distance is equal to the image distance. It was pretty exciting, wasn't it? All right, a couple of conceptual questions about looking at images in plane mirrors. Again, I would advise you to pause the presentation and make your best guess before moving on. Here, we're actually not going to answer the question. We're going to wait 2 slides until we derive what the answer is, but you should still note what your intuition is at this stage. So if you stand in front of a plane mirror and you observe your full image, meaning you can see the top of your head and the bottom of your feet, what is the minimum height of the mirror to be able to accomplish that? Do you need it to be less than half your height, exactly equal to half your height, more than half your height but less than your full height, or more than your full height? Second question, if you look in a plane mirror and you stand in front of a full-length mirror and you're just able to see your full image in the mirror, so the mirror is just long enough to see from the top of your head to the bottom of your feet. If you step back across the room, what are you going to see? Are you going to see now the image of yourself much smaller than the space allowed by the mirror, the image of yourself still equal in size to the space allowed by the mirror, or the image of yourself taking up much more space than is allowed by the mirror? So again, take your guess. We'll answer that question shortly. To answer the question, let's actually think about what happens when light travels from parts of our body that allows us to see those images of those parts of our body in a mirror. So I've given you a blank in the presentation. I would encourage you to sketch the lines along with me, but I'm going to switch over to this slide, which is where I've sketched the lines. So how do you see the top of your head in a mirror? Well, light reflects off of the top of your head in all directions, but the one that allows you to see the top of your head is the light that comes from the top of your head over to the mirror and then back into your eye. And it follows the law of reflection over here, where the angle of incidence equals the angle of reflection. That means, by the way, that point of the mirror lines up with a point on you that is halfway between your eyes and the top of your head, and that becomes important shortly. How do you see the bottom of your feet? Same kind of idea. We have a beam of light, or a ray of light rather, that comes from the bottom of our feet. Again, light is bouncing off our feet in all directions, but I'm just thinking about this one particular path of light. Bounces off the mirror and into the eye. And for both of those, to the observer, it looks like this one that came from the top of your head actually came from this location back behind the mirror. And the one that came from the bottom of your feet, to the observer, looks like it came from a position back behind the mirror as well. And so you see the image of yourself back behind the mirror, but that also tells you how tall the mirror needs to be in order to see your image. It needs to be from here to here. How tall is that relative to you? Well, we previously mentioned that this point where reflection occurs is parallel to a point halfway between the top of your head and your eyes. This point where you need the bottom of the mirror corresponds to a point that's halfway between the bottom of your feet and your eyes, and that means you need a mirror that is exactly 1/2 your height in order to see the full length of your image in the mirror. So that answers the first question, and it actually answers the second, because notice that in none of this conversation did I say anything about how far this doctor is from the mirror, and so it doesn't matter where you are. The same principle applies. If you see the full height of your reflection in the mirror when you're standing close to the mirror, you will still see the full length of your reflection in that mirror when you step back across the room. It'll appear smaller, but that's because you're further away from the mirror, and the image is therefore further away from the mirror, but it'll take up the same amount of real estate in terms of the height within the mirror as it did when you were close. Now we transition over and talk about spherical mirrors. So again, planar mirrors, the surface is flat. Spherical mirrors, the surface is curved, and so you can imagine cutting a little chunk out of a sphere that reflects light. If you have a inside surface that is polished, we call that a concave mirror. If you have an outside surface that's polished, we call that a convex mirror. So a concave mirror takes light and bends it down toward the center of that system, whereas a convex mirror takes light and bends it away from the center of that system. Well, for both of these, we can define the center of curvature to lie at a point we'll label C on this diagram. It just means when I made this sphere, it had a middle. Where was that middle? Well, that middle was at point C, and that point C was a radius of the sphere away from the outside edge, which is where we cut the mirror out of. The principal axis is just a tool that allows us to do some ray tracing. It's a line that passes through the center of curvature and through the center of the little chunk of mirror that we're thinking about. So spherical mirrors have the property that when light strikes those spherical mirrors, it converges the light down to a common point. So sometimes these are called converging mirrors rather than concave mirrors. If you have an object that's really far away, and we say infinitely, but it turns out a few meters or more works out great for this, the light coming into the mirror is essentially parallel to the principal axis. So light that comes in on top of the principal axis gets bent down. Light that comes in below the principal axis gets bent up. The point where they converge we define to be the focal point of the mirror, and the length from the mirror out to the focal point is defined to be the focal length of the mirror. So the focal length can be shown to be 1/2 the radius of curvature. The geometric argument goes something like you have a ray that comes in, gets reflected at point A down through the focal length. The angle of incidence has to equal the angle of reflection, so these two angles are equal to one another. But that is also equal to the angle formed over here by the triangle formed by the center of curvature and point A where this hit and point F. And that means that the focal length here, if you assume this ray creeps down towards the center point, approaches 1/2 of the radius of curvature. So sometimes in particular problems we know what the radius of curvature of the mirror is and we have to figure out what the focal length is, or vice versa. If in a spherical mirror you have rays that are further away from the center of the mirror or further away from this principal axis that we've constructed, they don't actually all get reflected through the same point. And the further away you get from the center, the worse and worse and worse it gets. So this is known as spherical aberration. You make a bigger mirror and it collects more light, but it doesn't focus it as well because of the curvature of the mirror. Well, you can take care of that problem by grinding your mirror into a different shape and actually making it parabolic. And that better focuses the light on one point. However, all of the geometry that we're going to assume in this presentation and the algebra that we're going to derive is based on thinking about the mirror as being a spherical section and not a parabolic section. So there are algebraic ways to solve these mirror problems, and we'll show that in just a couple of minutes. But there are also geometric ways to solve these problems, and the geometric methods are known as ray tracing. We're going to trace the path of rays of light that go from somewhere on an object and see what they do when they interact with the mirror and where they all converge together to form an image. Now you can draw any ray that you want to off of an object, but it turns out that there are 3 or 4 rays that are easier to draw than others because they behave in a very predictable way and we don't have to do a lot of precise angle calculation to work out what they will do. So the 3 convenient rays that you can draw when you're talking about a converging mirror or a concave mirror are: number 1, a ray that is initially parallel to the principal axis and then gets reflected back through the focal point. So here's my ray coming in parallel to the principal axis and going back through the focal point. Number 2, a ray that passes down through the focal point and then back parallel to that principal axis. Again, this ray 2 is essentially the inverse of 1. 1 comes from the definition of the focal point. 2 comes from the definition of the focal point sort of flipped around. Anything that goes through the focal point would have to be reflected back out parallel to the principal axis because it would still have to obey the law of reflection at whatever point of the mirror it strikes. There's a 3rd ray that you can draw. If you go from the top of the object, you can draw a ray that lines up with the center of curvature, heads towards the mirror, and because of the definition of the center of curvature, this line is going to be perpendicular to the surface of the mirror. That means the reflected ray is going to head back in the exact same direction that it came from and back through the center of curvature of this mirror. So let's do that. I've got a couple of examples of ray tracing here. Again, I've given you this blank in the slide presentation so that you can hopefully trace along with me as we do the ray tracing on this concave mirror. Here goes. A couple of notes. Here's my object, this pencil. What does its image look like when it is reflected in the mirror? Well, you do not have to do this, but you can cut your work in half by putting one edge of the object that you're doing the ray tracing for on the principal axis. What does this do? Well, any rays that I would draw from the eraser end of this pencil would actually just all pass along the principal axis and converge at some location along the principal axis. So I already know that the location of the image of the eraser is going to lie on the principal axis. I don't know exactly where it's going to be, but if I can find the location of the image of the tip of the pencil, the location of the eraser will be right along line with it. So I'm just going to find the location actually of the image of the tip of the pencil and then deduce what the image must look like from that. So here's one ray. It goes parallel from the tip of the pencil until it strikes the mirror, and then it's reflected down through the focal length, the focal point rather, of that mirror. One ray is not enough to deduce where the image is formed. But you can draw another ray. So here's a second ray that goes from the tip of the pencil down through the focal point and then gets reflected back parallel to the principal axis, and 2 rays is in fact enough to deduce where an image is formed. So those 2 rays are coming together right here. This is what I suspect will be the image location for this pencil, but it never hurts to draw a 3rd ray and verify that. So here's a ray that passes from the tip of the pencil through the center of curvature of the mirror, strikes the mirror, and then heads back in the opposite direction, and it indeed passes through that same point. You may have noticed, of course, that the ray that I drew goes way down below the mirror, but there's nothing magical about the mirror actually in this drawing. In fact, if I drew a straight line right where the mirror lies, I actually get the best geometric answer to this problem. And so you don't have to be confined to the actual space of a mirror if you're doing any ray tracing. You can use anything along a line that would pass through the center of that mirror and be perpendicular rather to the principal axis. The 3 rays that I drew came together at this location, so that tells me the image of the tip of the pencil is formed here. I already deduced that the image of the eraser of the pencil forms along the principal axis, so the image of the pencil looks something like this. And we can go back to the ideas that we listed for a plane mirror and say, are these things still the same? Well, is this image upright or inverted? In this case, it's inverted because the image is flipped upside down relative to the original object. It is also not the same size as the object. In fact, it is reduced, and we're going to subsequently talk about the concept of magnification. But this image is smaller than the object that formed it, and it is real, meaning it is in a location where actual rays of light are reflecting and coming together. I could put a piece of film or a screen right here at this location and see or record the image of the pencil at this location. Let's do the same thing with a convex mirror. Notice now in a convex mirror the focal length and the radius of curvature point are behind the mirror. And here's the one that I've done the tracing on. So if I have a ray of light that leaves the tip of the pencil, it strikes the mirror, but instead of being reflected down through a focal point, it's reflected away, but as if it came from the focal point on the other side. So if you're doing this with a ruler, you would line that point up with the focal point and draw this line that is going away from the focal point. A second one, and I've got these builds slightly out of order here, would head down toward the focal point and go back in the direction that is parallel to the principal axis. Here's where I said we got these out of order. So let me just draw that one back parallel to the principal axis. Well, this first one that got reflected up here actually appears to have come from the focal point. And so knowing what the answer is going to be in this particular situation, I've gone ahead and traced that extension of that ray back behind the mirror, even though there's no actual light coming from that location. Similarly, this second ray that came in toward the focal point and then was reflected back parallel to the principal axis appears to have come from a point back here behind the mirror. And on this side, these 2 rays of light don't come together, and they won't. So I'm not going to form a real image here. I will, however, form a virtual image because these rays of light appear to have come from a common location behind the mirror, and that is the image location in this particular case. I'm technically done, but it doesn't hurt to draw a 3rd ray and see if it converges in the same location as the first 2. So I head toward the center of curvature of this system. It would bounce back directly away from the center of the curvature of the system in the other direction, but that ray appears to have come from back here behind the mirror, and yes, indeed, that comes from the same location as the other 2. That means the image of the pencil is formed back here behind the mirror. How do we characterize it? Well, it is upright, so that just means it's on the same orientation as the object that formed it. It is reduced in size, so its magnification is less than 1. It's smaller than the object that forms the image. And it is virtual, because it's not actually located at a place where real rays of light are coming together. We couldn't put a piece of film there. We couldn't put a screen there and see an image of a pencil. All we can do is observe from this side of the system and see where the image of this pencil appears to form behind the mirror. we can deduce a mirror equation for doing the similar kind of analysis, but now algebraically rather than geometrically. So to do that, we think about two rays. One of the rays here in diagram B is one that we already thought about. The ray that comes off of the top of the object, passes through the focal point, and then is reflected back parallel to the principal axis. But a second ray, and this wasn't one of the three principal rays we did before, comes off of the object, strikes the center of the mirror, and is reflected off at the same angle, following again the law of reflection here. It doesn't pass through the focal point or anything like that, but it's a legitimate ray, and in both of these diagrams I'm forming two similar triangles here. So the two shaded triangles in diagram A are similar to one another because they share common angles. This angle the angle of incidence has to equal the angle of reflection. They both have a 90-degree angle, and that means these third angles are also equal to one another in those triangles. Same thing down here, these two triangles are similar to one another as well, for the same kind of reason. These angles, these opposite angles of two intersecting lines have to be equal. They both have a 90-degree angle, so the third angle has to be equal as well. From diagram A, we can say that the ratio of the object height to the image height equals the object distance to the image distance because these two triangles are similar. We make the image distance negative, however, because in this particular system the image is flipped upside down, and so that gives us a negative image height relative to the object height. From diagram B, we can say that the same ratio of object height to image height, again with the image height being negative, must equal the ratio of these sides of the triangle. So this side of this particular triangle is the object distance minus the focal length, and this side of the similar triangle is the focal length. Why am I doing this? Well, I've got the same thing on the left of both of these, and that means the object distance over the image distance must equal the object distance minus the focal length over the focal length. Now we're just going to do a bit of manipulation. Focal length over focal length is 1, so we can rewrite this slightly. And then I can divide through by the object distance to get 1 over the image distance equals 1 over the focal length minus 1 over the object distance. And conventionally, we put the term involving the object distance on the left side of the equation so that we form the mirror equation, which says 1 over the image distance plus 1 over the object distance equals 1 over the focal length of this particular mirror. We similarly can define what we mean by magnification. Again, I've got my two diagrams where I've labeled the triangles and the various rays that we're thinking about forming these triangles. The magnification of an object is defined to be the ratio of the image height to the object height, and it's positive if the image is upright, negative if the image is inverted. So the definition is simply image height over object height. In this particular case, I would say the image height would be negative, so I'd plug in a negative number here, positive number here, and I would get a negative magnification, which would tell me that the image is inverted relative to the object. But it must also equal the negative of the image distance over the object distance. In this particular case, both the image distance and the object distance are positive numbers, and we'll talk more about that shortly when we talk about sign conventions. But that would also produce a negative magnification for this particular situation. Here, in fact, is the convention, the sign convention discussion. So one of the things that gets people messed up in solving these mirror kinds of problems are, how do I know this is positive or negative or what have you? Well, it turns out that only one of them you have to assign, and it's assigned by the convention that, I don't know who made it up first. The rest of them can be deduced, but for some people it's handy just to have this table anyway that they can refer to. So for the spherical mirror, the focal length, you have the focal length, and the focal length is positive when you have a concave mirror and negative when you have a convex mirror. So this is the one that's just assigned. To fit the mathematical structure that we've worked out, we have to say concave mirrors have a positive focal length, convex mirrors have a negative focal length. The rest can be deduced from what's going on. The object distance is positive when the object is real. negative when the object is virtual. If you only have a single object with a single lens or mirror, the object distance is always positive. The only times we run into this concept of virtual objects are when, for example, we have two mirrors, so I form an image of my object in one mirror, and that image then acts like the object for reflecting through the second mirror. And in some of those situations, that image that's now turned into an object can be in a position that means it has to be considered to be virtual. If we talk about any of those in those problems, we'll talk more about it in detail there, but I think you are fairly safe to assume that object distances will nearly always be a positive number. Image distances, however, will be positive or negative depending on what happens in a given situation. An image distance turns out to be positive if you have a real image, and negative if you have a virtual image. Again, a real image is formed where real rays of light converge, and a virtual image is formed where rays of light appear to have come from but do not actually exist. If you know the focal length of a mirror and you know where you place the object relative to the focal length of that mirror, you should be able to predict algebraically where the image is formed. If you get a positive answer, that would tell you the image should be formed in front of the mirror. If you get a negative answer, that tells you that the image should be formed behind the mirror. Finally, magnification is positive if the image is upright and negative if the image is inverted. We've said this previously as well, but for some people it's helpful to have these all in one table. So let's do a practice problem with the idea of a curved mirror. Here's a question about a reflected coin. If you take a coin and you place it 8 centimeters in front of a concave mirror, and the mirror produces a real image that has a diameter that is 4 times larger than that of the coin, what's the image distance? How far away is the image from that mirror? And what is the focal length of the mirror? All right, let's work that out. My apologies, I forgot to put builds in on this slide, but I'll just talk through it in order. I always draw a sketch. I'm not sure if a sketch is helpful here, but the coin is 8 centimeters from the mirror. And to get the image distance, I actually turn to the magnification equation because the magnification equation relates the magnification, which I know, that's the 4 times larger, to the object distance, which I also know, and the image distance, which is what I'd like to find out. Well, if it forms a real image in a concave mirror, you may know that if you make a real image in a concave mirror, it always ends up being flipped upside down. And so that means the image height is going to be negative relative to the object height. Or a real image is formed when the image distance is positive, because the real image is formed in front of the mirror, and a positive image distance over a positive object distance will also yield a negative magnification. Bottom line, the magnification has to be negative, so it's -4 in this particular case, and that means the image distance is equal to the negative of the magnification, rather, times the object distance. I've got to keep track of all my negatives here, but the image distance is negative of the magnification, which itself is negative, times the object distance. End result is a positive number, 32 centimeters. And I expected it to be positive because the problem told me that this image was real. If you messed up and didn't get the negative of the negative, of course, you would have predicted negative 32 centimeters and may have gone on at that point. So when I did B, I actually showed what would you get with the wrong answer and what would you get with the right answer. We'll talk about those momentarily. What's the focal length of the mirror? For that, I'm going to use the mirror equation, which relates the focal length, the image distance, and the object distance. Well, let's say I'd done A wrong and I had a negative focal, or negative image distance rather, then 1 over the focal length would equal 1 over negative 32 centimeters plus 1 over 8 centimeters. If I solve that all out, I get a positive number, 10.7 centimeters, which I expect the focal length of a converging lens to be positive. But the problem would be that I would find a focal length that would be greater than my object distance. And if you've ever played around with a concave mirror, if you get the object really close to the concave mirror, it forms an upright but virtual image that is located behind the mirror. And we're told that this image is real. So that's another check on this. The image distance can't be negative, and if you make the image distance positive as it is, you find that the focal length is 6.4 centimeters in this case. And that works because this coin is now held further from the mirror than the 6.4 centimeter focal length of that mirror. A conceptual question involving the same kind of system. If you have an object that's placed 2 meters away from a concave mirror, and the mirror has a focal length of 1 meter, the image formed by the mirror is going to be real or virtual, and larger, smaller, or the same size relative to the object. Again, I would encourage you to pause the presentation and think of your answer before listening to mine. My answer is that it is real and the same size as the object. Here's how I worked that out. I know that the focal length of this concave mirror is 1 meter, and I know that the object is 2 meters away. And so I can calculate an image distance using the mirror equation. So 1 over 1 meter equals 1 over the object distance, or 2 meters, plus 1 over the image distance, which is unknown. Well, if you solve that, you get an image distance of 2 meters, and it's a positive number. The positive number tells me that the image is, in fact, real. There's another way you can do it, because if you've thought about and played around with concave mirrors enough, you realize that anytime you hold an object further from the mirror than the mirror's focal length, you form a real image. And anytime you hold an object closer to the mirror than the mirror's focal length, you form a virtual image. So in this case, where the object is further away than the focal length, right away, because I've been doing this for 20 years, I expected that the image formed by the mirror would be real. Given that we worked out that the image distance would be 2 meters and the object distance would be 2 meters, the ratio of image to object distance is going to be 1, and that means that this object is going to be the same, or the image rather, is going to be the same size as the object that formed it. I'm going to talk briefly at the end here about the concept of refraction. If you've ever been bored in a restaurant and stuck your utensils down in your water glass, you might have observed something that looks like this, which is interesting to people like me at least, because it looks like, the spoon is no longer straight, it's bent or disjointed or disconnected here in some fashion. What's going on there? Well, this is an example, and there are many of these examples, of refraction, which we've actually introduced at least partially the physics behind. It comes from the idea that light travels at different speeds in different materials. So when light goes from air into glass, or glass into water, or water into air, or whatever direction it goes, when it goes from one medium to another, it changes speed. And when light travels from one material to another, it not only changes speed, it changes its wavelength, and in changing its wavelength, it gets bent or refracted. Here's an example of that can help some people think about what's going on here. And this has nothing to do with light. It has to do with four-wheeling in the grass and the mud. If you're driving along here on your four-wheeler, and here are the axles, and out here are your tires, there's the 4 tires. You're driving along a nice straight line, but you're going to hit the boundary between the grass and the mud at an angle. What's going to happen there? Well, the front right tire of your four-wheeler hits the mud first. It starts slipping, and that results in the whole axle turning to a new angle relative to what it was traveling at before. When the second axle hits, the same thing is going to happen, and the end result is your whole four-wheeler has turned and is now traveling at a different angle with respect to the boundary than it was when it was on the grass side. You can, by the way, do this whole premise in reverse. If I'm going in the mud and I approach the boundary, this tire is going to hit the grass first. It's going to get better traction, so it's going to start covering more distance with time, and it's going to turn the whole axle to the left. And so you can actually reverse this path in thinking about what's happening here. So if you replace the concept of axle with wavefront, this would predict that when wavefronts hit boundaries, the wavefront itself gets bent, because if the wavefronts hit at an angle, whichever portion of the wavefront enters the slower moving medium first will start to slow down. The other portion of the wavefront that's still in the faster moving medium is still going along at its regular speed, and that has the effect of turning the whole wavefront. For any of you that have done marching band in your past and ever turned a corner while trying to march in line with a bunch of people playing instruments, same kind of idea. The person on the inside of the turn slows down first, and the person on the outside of the turn goes faster for that whole line to turn. So, in the interest of survival skills that you may need sometime in your future, what happens if you are ever trapped in the wilderness, you have a spear, but you are otherwise cut off from civilization and you would like to eat? Well, you spy a fish in a pond. How should you go about acquiring said fish using your spear? Well, you see the fish because light is traveling in all directions, but some light is bouncing off of the fish and moving into your eye. However, that light takes a path that takes it up to the surface of the pond, so it's going through a water-air boundary, and when it does so, it gets bent, in this case because it's going from something that has a higher index of refraction or is more optically dense to something that has a low index of refraction or is less optically dense. It gets bent away from the line that's perpendicular to the boundary and enters your eye over here, making you think, by the way, that the fish lies along that straight line here higher in the pond than the fish actually lies. Moral of the story, next time you're spearfishing, aim low from where you see the fish appearing to be within the pond. Wrap this up by a reminder of the concept of the index of refraction. We've already introduced this in class, but the index of refraction, n, of a given material is the ratio of the speed of light in the vacuum, which we use the symbol c for, to the speed of light in the material, which we use the more generic v for. So the index of refraction is the speed of light in a vacuum over the speed of light in the material, or c over v. And you can also show that this means it is equal to the ratio of the wavelength of the light in a vacuum to the wavelength of the light in whatever material it is you're studying as well. And here are some indices of refractions for some common materials. Notice that all of the gases have an index of refraction that is very nearly 1. And so we sort of ignore the bending of light when we're talking about light traveling from the sun through the vacuum of space into the atmosphere and through the air and or carbon dioxide pockets or what have you. Unless you're doing some precise measurements, you don't need to worry about the indices of refraction of those gases. But anytime you're in a transparent liquid or solid, those indexes of refraction are significant enough that you cannot ignore the bending of light in those. And glass is about 1.5. Water is about 1 1/3. Diamond bends light a lot. 2.4 is the index of refraction in a diamond. I'm not sure if that directly relates to the sparkliness of a diamond, but a diamond is a good bender of light nonetheless. We'll pick up more on this index of refraction in the next and final lecture for this class, dealing with Snell's law and then moving into lenses. But this concludes this particular presentation on reflection, refraction, and the formation of images. Again, I'm hopeful, yes, that this is a useful resource for you. If you've seen any errors in the presentation or have any questions about what you've seen, I would certainly encourage you to point out those errors or ask those questions. Thanks.